Hello everyone, today I'm going to do another retrosynthesis video. I'm going to be tackling this molecule on the screen now. I'm pitching the discussion at kind of undergraduate level. If you do enjoy the video, do give it a like and consider subscribing to my channel so you know when more videos drop. Okay, I've got this molecule here that looks a bit complicated on first sight because it's quite big. But in fact, if we analyze it for functional groups as normal, we'll see that there's actually not very much going on here. So we have an amine at the top, and there's also an ether and a benzene. Now these two functional groups are quite stable, so they shouldn't really be my first disconnection. So that makes my first disconnection choice quite easy to some extent, so I must go for the amine. And my default type of reaction for this type of disconnection should really be a reductive amination. There are of course many other ways of making amines, but this is a really reliable one. So a reductive amination disconnection requires me to break a CN bond. And in the molecule I'm looking at, there's 3 of those that we could choose. So we should just take a pause and have a think about which one would be the strategically most useful one to go for. Now I think it's this one here, the one that connects the nitrogen to the ring system. So I'm going to propose my first disconnection across here. And the reason why this is so good is it breaks the molecule quite quickly into 2 reasonably sized chunks of about the same size. So in a forward synthesis, this would add convergency. The other advantage of this disconnection is it breaks at a branch point, and breaking at branch points always reduces complexity quite quickly. So it's a useful strategy in retrosynthesis. So this reductive amination disconnection will take me back to a ketone to represent the ring component and another amine. So thinking about the type of disconnection we might use in a forward synthesis, we could go via some sorts of condensation, like via an iminium ion, and make sure we have a reducing agent on hand. So first, just to deal with that amine, well, because it's an amine, as we just said before, our default should be to go for a reductive amination disconnection. And there's a choice of 2 CN bonds here, on the left or the right of the nitrogen. Doesn't really matter which way you go, it just depends on what you've got in the lab, I guess. So if I disconnect on the left-hand side, that will take me back to propanal as a carbonyl component and benzyl amine as my other component. And I can just form the imine between those two by condensation again and make sure there's a reducing agent around to convert the imine into the amine. The alternative would be to disconnect on the right-hand side. And in this case, I just switch the functional groups over. That will take me back to propyl amine and benzaldehyde here. I think my preference is to go for the bottom combination of reactants here. And that's largely because benzaldehyde is reasonably easy to handle in the lab. Propyl amine is quite cheap, and I'm very likely to have it kicking around anyway. Whereas for the first option, I might be worrying about my propanaldehyde being a bit wet. Small aldehydes are pretty unhindered and can take on water quite easily to form the hydrate. So I might need to purify it by distillation before I use it, for example. So I'm just saving myself a bit of time because I think the benzaldehyde will be a bit more stable to forming hydrates, and I'll be able to use it straight from the bottle. Okay, so next I need to turn my attention to the other component, the ketone. Now there's actually a few things that we can do here. The first thing that I'll note is disconnecting off the methyl group isn't really going to make my life much easier here because I'd just be functionalizing right on the end of an already still quite complicated molecule. So I'll ignore my ether disconnection option. So we mentioned there was a benzene in there before, and I'm just going to have a think about my different options for attaching functional groups to benzene rings. Now I could have a think about this bit here. So how do I add an oxygen onto a benzene ring? Well, there's not so many classical ways of doing this, so I think I'm not going to cut this one. But one thing I'll note in passing is having an oxygen substituent like that with its lone pairs can often be quite useful in benzene chemistry because the group serves as a pi electron donating group. So in reactions where benzene reacts with an electrophile, this will have an ortho-para directing effect, and that's due to delocalization of these oxygen lone pairs into the aromatic system. And just looking at the other substituents on here, they're both examples of benzene being attached to a carbon. And I know some useful chemistry for forming those types of bonds in the form of Friedel-Crafts chemistry. And this could be perhaps either an acylation type reaction or an alkylation type reaction. We'll just have to see what we disconnect back to. So one of the first things we might think about is disconnecting this carbon-carbon bond that's para to the oxygen. Because it's a para-directing group, that seems like a legitimate way to go forwards. But we run into a problem straight away, in that if I do this disconnection here, I would require a primary carbocation in my Friedel-Crafts alkylation reaction, and those aren't observed in solution in any reaction. In fact, we risk some sort of rearrangement, and we'll get some completely different product. So that actually leaves me with no choice of my first disconnection. I must go here and do a Friedel-Crafts acylation to form the new carbon-carbon bond. And I just want to have a quick check that that idea might work. So the disconnection would take me back to this acid chloride, And the idea would be that I'd add some sort of Lewis acid, such as aluminium trichloride, that would attach to the chlorine lone pairs to make that a really good leaving group, and that will allow me to generate the acylium ion, which is sufficiently electrophilic for a benzene ring to break its aromaticity. So actually what we see here is this bond-forming reaction will be intramolecular, and I need to convince myself that I will get reaction at the correct position. Now I think this will be fine because although we have the lone pair on the oxygen wanting to direct into the ortho position, the para position's already taken, trying to form a ring between here and here is too much of a stretch. This alkyl group is pointing away from that position. The benzene ring is flat. There's just no way we'll get enough wiggle room for this to reach over. So in fact, the only plausible mechanism here is to react in the meta position relative to the oxygen lone pair. And forming a six-membered ring isn't particularly controversial in organic chemistry. So I think all is good for this reaction. So just as a reminder, the reactant I needed for that step was an acid chloride. Now, when we're thinking about disconnections, we should always worry if we have a reactive functional group in the sequence. We should disconnect it pretty quickly so that we don't have to carry it through lots of other steps where there might be competing reactivity. So I could do some sort of functional group interconversion. And one of the easiest ways to make an acid chloride is to disconnect back to the carboxylic acid, because I could use something like thionyl chloride, SOCl2, or PCl5 to change out the oxygen and substitute it for a chlorine. So now it looks like we're making some progress here. We have a para relationship here, so hopefully we can do some sort of carbon-carbon bond forming reaction at this position, which could be directed by the methoxy group. But we haven't really solved our problem of the primary carbocation. I can't do that disconnection at present. And now I just need to bring in a bit of my experience to make a slightly off-the-wall disconnection. So Friedel-Crafts alkylations are a little bit unreliable in the grand scheme of things. You have to form a very high energy intermediate in a carbocation, and there are often many competing reactions that can go on if you generate something like that. But Friedel-Crafts acylation reactions are way more reliable. The acylium ion is implicated, and you can normally generate it exactly when and where you want it to be. So I'm going to pretend that the Friedel-Crafts alkylation reactions just aren't really an option for me, and I'm going to do another functional group interconversion where I'm going to strategically add a carbonyl in this position down the bottom. This will allow me to disconnect this bond here and do a Friedel-Crafts acylation. So there's a bit of an odd disconnection and requires a bit of experience to spot these types of things when they might be useful. It's often a last-ditch resort as well. But I'm going to do this based on the fact that I know a few possible different reactions that I can use to completely remove a carbonyl and replace them with hydrogens here. So some of the most commonly used options in sort of classical retrosynthesis would be to use the Clemmensen reduction. This just uses zinc metal in the presence of an acid as pretty much a blunt tool reducing agent. However, the ketone is the most electrophilic thing on my starting material, so would be susceptible to this type of reduction. Another common trick is the wolff-kishner reduction, in which you use hydrazine and potassium hydroxide at a high temperature. This goes via a hydrazine that then can thermally decompose to give off nitrogen gas. So just thinking about what might be most appropriate for my substrate, well, I do have a carboxylic acid up here, so it's maybe not a good idea to be boiling this up in potassium hydroxide, which is a good base, whereas it will be totally tolerant of acidic type conditions, such as in the Clemmensen reduction. So I think my initial preference would be to try to go for this top one. Now, there are many other ways of removing carbonyls directly from molecules, and they all have various chemoselectivity issues associated with them. For example, you could form the dithiene and hydrogenate to break carbon-sulfur bonds, or we could go via some sort of elimination hydrogenation pathway, but I don't want to make an exhaustive list here. Okay, and now we're in a position where we can finish the synthesis. I will disconnect in this para position and do my Friedel-Crafts acylation to form a new carbon-carbon bond. And that will take me back to something that looks a bit like this. So usefully, the aromatic system here, this is readily available and is very cheap. This is anisole. And we note that it has the correct para-directing substituent for the Friedel-Crafts reaction. Now, this other reagent, we might want to just be a bit more clever, really. The plan for a Friedel-Crafts acylation would be to try to make this chlorine leave to form the acylium ion. But noting what we've got at the top of the molecule, we've got essentially something that could be an acetate leaving group. So we can be a bit sneaky here with a reagent that might represent this. And I could use this cyclic anhydride to represent that reactivity. It's also very cheap and readily available. This is known as Succinic Anhydride. And just to see how that might work in a Friedel-Crafts acylation, When I add my Lewis acid, say AlCl3 again, I'll activate this as a leaving group. But actually we could form the acylamine directly. And my benzene ring will be able to attack this electrophilic center, but leave this top bit completely untouched. That acetate group's going to stick nicely to that aluminium. Aluminium oxygen bonds are pretty strong. And we're not going to see that molecule fall into bits to form a second acylamine, for example. It will just hang around in the reaction flask. So once I've done my attack with my benzene ring, I should just get mono-substitution, and then with an aqueous acid workup, I should be able to get rid of the aluminium and leave me with the carboxylic acid that I wanted in the first place. Okay, then that's me done for today. I really hope this video was useful, and if you enjoyed it, please do give it a like. I'll be making some other videos along this sort of lines that will showcase different ways of using disconnections. So do please click that subscribe button if you want to not miss out.